All right, so hi everyone, welcome to our materials seminar, and we are very happy to host Professor Claire White today. She's at Princeton University in the Department of Civil and Environmental Engineering, and she has won a bunch of awards. I just checked quickly and I was very impressed. I'm not going to read them out, but we are very happy that you make some time today and talk with us. As always, please post your questions for our speaker in the chat. And then after Claire's talk, I'm going to call you out individually and then you can ask your question again. And without further ado, thank you. Welcome to this virtual seminar. And we're very excited to hear about the material science of sustainable cements from you. Floor is all yours.
Thanks, Christina. I'm very happy to be here today, albeit remotely, as most is happening at the moment due to COVID. Very much appreciate the invite to come and present. So it's a very generic title that I've put up, the Material Science of Sustainable Cements, but hopefully I'll be able to convince you that there's a very strong incentive to understand the material science of cement materials, and especially new types of cements, so that we can predict how they're going to perform long term. Especially given that it's kind of a chicken and egg game at the moment with if you're trying to make cement more sustainable and say changing chemistry of the cement, we can't wait 50 to 100 years to get data on its long-term performance, given of climate change at the moment and wanting to reduce CO2 emissions. So let's see if this is going to work. It's not, so I might as well just use the keyboard then. So the incentive for sustainability in engineering materials comes from the fact that if we look at construction materials, concrete and steel are the two top engineering materials that contribute CO2 emissions to the environment. And so if we look at cement manufacturing, cement is responsible for about 8% of all anthropogenic CO2 emissions. And then if we look at steel, it makes up about 7% of all anthropogenic CO2 emissions. So in the past, there's been a lot of focus on energy and electricity production when it comes to climate change. There's also been a lot in terms of the transportation sector, heating and cooling of buildings, those kind of things. But what's happening now is there's very much an interest in, can we decarbonize industries, and industries that tend to be quite CO2 intensive, which cement manufacturing makes up one of those. So if we look at paths forward in terms of how to reduce CO2 emissions associated with these industries, carbon capture and storage plays a huge part. If you look at the techno-economic assessment reports that are coming out from the various organizations, there's always seems to be quite a bit on carbon capture and storage and utilization nowadays. But there's its own technical hurdles associated with CCS. Comes down to cost of capture materials and adequate storage locations as well. So when it comes to concrete, we really need to look at alternatives in addition to other ways to mitigate emissions associated with the technology. Now, if we look at steel, this is just a bit of a side interest, but if we look at steel, there is big interest in looking at, can you use hydrogen as a fuel instead of, say, fossil fuels to produce steel. And then there's also been interest in carbon fiber reinforced polymers as well, say with wind turbines. Instead of using metals, they've been shown to perform very well. But in terms of if we're thinking about from a construction standpoint, say buildings, bridges, those kind of things, the carbon fiber reinforced polymers are quite expensive. However, they are options. So today what I'm going to talk about is I'm going to focus on the cement side of things, and specifically blended types of cements, so cements that do still contain Portland cement powder and what people are looking at, and then also some alternative types of cements as well. So in terms of what my group focuses on, we do a lot on the cement side of things, but we also do quite a bit on carbon capture nowadays. looking at new types of materials for carbon capture that have lower energy requirements for rejuvenation, because a large part of the cost of CCS is actually the capture materials themselves and their rejuvenation. And the way that my group goes about it is we're really focused on the sub-micron length scale. So we use material science approaches to discover, understand, and manipulate fundamental behavior of these types of materials so that we can optimize macroscopic performance. And we do it both through a combined simulation approach and experiments as well. So today I'm going to present both types of approaches where we've been using density functional theory for some research, and we've also been using some experimental characterization techniques. And so as with all kinds of materials, understanding what's going on at smaller length scales helps inform how the material is performing at more of a macroscopic scale. And so what we do in terms of the research and the findings we achieve, we hope is helping inform how these materials can be used successfully in industry and help incentivize using more sustainable materials. So to give you a bit of an overview of the types of techniques that we use in my group, we use on the simulation side of things quite a bit of DFT modeling, and we also do coarse-grained computational techniques as well. And then on the experimental side, we do quite a lot of synchrotron and neutron characterization techniques, often because the materials we have are disordered or amorphous, which makes conventional like XRD, it's useful and we do use it quite extensively, but it's harder to tell what's going on with the amorphous phases. And then especially with the cements, we're interested in pore structure. Degradation of concrete is largely controlled by how permeable the concrete is. And so understanding the pore structure of the material is very important. And we've used a variety of means to look into that side of things to not only understand the pore structure, but also permeability. And then we do dabble a little bit in some of the microstructure techniques, such as standard SEM. We do tomography, and then we've done a little bit of helium ion microscopy. And so we, depending on the question, the scientific question we want to answer, we use the appropriate techniques that are best suited to determining what we are interested in understanding. Okay, so let's move on to cement. And the first thing, in case you're not aware of where CO2 emissions come from cement manufacturing, we're going to go through that quickly. Then I'm going to give you an overview of where the industry currently is in terms of mitigating CO2 emissions and enhancing sustainability. And then we're going to talk about some of the key unknowns and how the research we're doing is helping to answer these key unknowns. So in terms of cement manufacturing, so what we use nowadays is Portland cement powder, and that gets mixed with water, and it's a binder that holds sand and rocks together, which makes concrete. So the Portland cement powder is not a natural material. It needs to be synthesized, and it's synthesized in cement kilns. And so what happens is you have a limestone source in a quarry that's right next to the cement manufacturing plant, and you also have a source of clays or silica there as well. This all gets processed and fed into a very high temperature kiln. There's a lot of reactions, solid state reactions that occur in this kiln that produces a material known as clinker, which then gets mixed with gypsum, which is a calcium sulfate phase, and that's essentially the cement powder that we use. And so what's going on in the kiln here is really where the CO2 emissions come from. Because we're digging out limestone, which is calcium carbonate, once you heat it past about 800 degrees Celsius, it decomposes into calcium oxide and carbon dioxide. And the carbon dioxide at the moment is going into the atmosphere. And then also to get to these really high temperatures, in the past, it's people have used petroleum coke. It's a very good fuel for these cement kilns. And so obviously with combustion of petroleum coke, there's CO2 emissions from that as well. And so if you look at the divide of how much CO2 is produced by the decomposition of the limestone versus how much CO2 comes from the fuel source, it's about 50-50. And then if you look at the amount of CO2 per ton of clinker that comes out of the kiln, you're about 800 kilograms of CO2 per ton of clinker. And so this is all based on the fact that limestone needs to be decomposed. So you get oxides that react with the other elements in the system, and also needing to get to high temperatures. So there's a lot of people working around the world on how to reduce CO2 emissions associated with this industry. And so there's 4 main areas that have been talked about, including by the International Energy Agency. There's the energy efficiency of the kiln. So can you mitigate waste heat from being lost? Alternative fuels, so biomass as an example. People are also looking into electrification of the kilns as well. On the concrete level, people are looking at what's called clinker substitution. So can we make the same amount of concrete using less Portland cement powder? And there's a lot of material science that goes into this, because there's a lot of empirical evidence that Portland cement concrete works well. We know how it works. You know, people are used to it in industry. They're happy to use it. But if you start changing the ingredients, then there comes about questions about, okay, what's its long-term performance? Is it going to degrade? How is it going to degrade? How does, if we substitute in other materials, how's that going to impact long-term performance? And so material science is very important for understanding what's happening to the individual phases that make up concrete when you're, say, changing the composition of the raw ingredients. And then the big one, which I've already mentioned, is carbon capture and storage. So that's a very big component that the cement industry is talking about having installed so that they can meet the CO2 reductions that they're aiming for. But also, there are alternative cementitious materials. Now, these are kind of seen as more disruptive because they don't include any Portland cement powder to make the concrete. It's a different type of chemistry. But the construction industry is quite conservative. I could spend 45 minutes talking about that, and I'm not going to. But because they're quite conservative, even if you have a material that's seen to work well nowadays, there are questions about long-term performance. And so part of what my group's doing is to try and show through fundamental research, if we better understand how these alternative cements behave, then we can better predict what's going to happen long-term. And so in terms of what my group does a lot of research on is these alternative cements, and I'm going to talk about one type today. And then we also do look at how clinker substitution impacts Portland cement concrete. And we're also working on materials for carbon capture as well. So before I get into the actual research that I'm going to present today, I'm going to make sure we're on the same page with terminology. Concrete has, there's one phase in concrete that essentially gives the concrete strength, and it's called calcium silicate hydrate gel. And people are still debating what is the structure of this gel, what are the properties of this gel, even though concrete's been around for 150 years. So it's a complex phase, it's disordered, it does have some ordering in there, but it's also difficult to study in concrete because there's over half a dozen phases that exist in concrete. So trying to isolate the calcium silicate hydrate gel is difficult. But you make this the calcium silicate hydrate gel is made when you mix Portland cement powder with water. It's a hydration reaction. Calcium silicate hydrate is one of the phases that precipitates out, along with other phases. There's 5 phases in the beginning, Portland cement powder. So it's a very complicated kind of reaction process going on if you're trying to track everything. And so Portland cement powder mixed with water is the glue that holds sand and rocks together in the concrete, and you end up with concrete. So what's happened is that originally calcium silicate hydrate gel was the main binder phase that holds concrete together. And up until about, I would say, 100 years ago, most concrete was mainly based on this gel in terms of the strength-giving phase. But in recent years, in recent decades, what's happened is that people have started substituting what's called supplementary cementitious materials into concrete, which changes this fundamental gel. It changes the chemistry of the gel, and so then it's possible that it's also changing things like its thermodynamic properties. Recently, people are now wanting to put ground recycled glass into concrete, which has a high sodium content often. So how does sodium affect the gel properties? And then even more so now, sodium plus aluminium in addition to the calcium silicate hydrate. So we have quite a good understanding of what's going on with the base calcium silicate hydrate gel. But as we are changing the chemistry of Portland cement concrete, we're also changing the chemistry of the gel itself. And we have relatively low understanding of how, say, sodium impacts the stability of Portland cement concrete. Now, my group does a lot of work on material called alkali-activated concrete. And this is where there's no Portland cement powder whatsoever. And you can make this a variety of different ways. You can make it using blast furnace slag. You can use coal-powered, fly ash from coal power stations, calcined clays as well. So there's industry byproducts that can be used. There can be processed natural products that can be used as well. They're usually very rich in aluminosilicates, not always rich in calcium. The aluminosilicate powders, you want them to be amorphous so that they react in a high pH solution. And so you're getting a similar binder that's holding sand and rocks together to make a material that looks and acts like concrete at a macroscopic level. But the fundamental binder that gives the concrete strength has differences to Portland cement concrete. So you can get ones that are very rich in calcium, and here it's called a sodium substituted calcium aluminosilicate hydrate gel. We're going to talk about this quite a bit today. If your aluminosilicate doesn't have much calcium in it, then you end up with what's called a Nash gel if you're using a sodium activator. So it's a sodium aluminosilicate hydrate gel. We also do a lot of research on systems that contain this Nash gel as well. But today I'm going to be concentrating on the Nash gel. It is important both for blended Portland cements, where sodium's going into it, and also for certain types of alkali-activated concrete. There is a general consensus that the Nash gel has similar types of local bonding environments to the original calcium silicate hydrate gel, but there's differences in terms of the silicate chain lengths. CSH gel has finite length silica chains. They're not infinite as shown here, but they are finite. Over here with the Nash gel, they are different. People have seen that from NMR, and we're going to talk about that today as well. And then the real question is, how does sodium disrupt, or how does sodium impact the CSH gel? Does it just substitute for a calcium and therefore it's happy to sit there, or, you know, 2 sodiums for a calcium? Or is there other stuff going on when sodium's incorporated into the structure? What I should mention is it's very important to keep in mind that concrete is a heterogeneous material across length scales. So although today I'm talking mainly about this binder gel that gives concrete strength, it's very important to understand that there are multiple phases that exist in concrete. How they're arranged relative to each other is very important. It's also a porous material. So you can't just study the material at one length scale to understand how it will perform macroscopically. You really need to be looking at the material across length scales. And so this is, if we've got an 8 micron size box, this is 8 microns. This is an alkali-activated slag where there's some gel that's forming with different compositions. There's a calcite particle. If we look down here in this region, which is over here, there's an iron silicon rich particle from the unreacted slag. There's another piece of slag over here as well. So that's at the micron length scale. If you look at about 100 microns or so, you can see the type of microstructure that forms where you've got partially reacted particles embedded in the matrix. And there's different kind of reaction fronts that have formed when the particles have been dissolving and the matrix type gel has precipitated out. You end up with some of these rings that form around some of the particles in the slag system, and people are studying why they form and what does that really mean about the reaction processes. And you can go to more of a macroscopic length scale, and then you've got interactions between rocks and sand and the paste itself. interfacial transition zone. There's a lot that goes on there in terms of how the interfacial transition zone impacts macroscopic strength. So I'm mentioning this just to make sure that it's clear that what we're doing at like a nanometer length scale is important, but it has to fit in the context of what's going on across length scales to explain macroscopic properties. So this is really the motivation for the research, is we don't have long-term performance understanding of new types of concrete or for alkali-containing blended Portland cement concrete, and this is hampering implementation in an industry. So there's the need to be able to predict long-term performance. I mean, this is kind of like where the multi-scale modeling comes into play. And so there is the role of fundamental research, including, say, molecular simulations and larger length scale simulations, to help inform what's going to, or predict what's going to happen long-term, to give an idea of, hey, these chemistry systems we might want to avoid because of such and such reasons, or these systems look really promising. Maybe we should be spending more time looking at these systems. And so specifically for my group, in terms of long-term performance, we're looking into atomic structure of the gels and thinking about how stable the gels are if we change chemistry, and potentially how that impacts long-term performance. And I'm not going to talk about it today, but we do also do quite a bit on pore structure of these materials and the new types of materials. Can we predict what pore structure will develop using coarse grained simulations combined with experimental techniques? So now we get to the interesting part, which is the first research question I'm going to talk about today, which is how can we study the impact of sodium on the stability of calcium silicate hydrate gel? So there's some already known facts about calcium silicate hydrate gel and where the sodium will go. So it's known that sodium wants to go into the interlayer region of calcium silicate hydrate gel. And so here's a schematic that's showing silicate tetrahedra connected. There's two calcium environments. This is a calcium oxide layer. And in here, this is the interlayer region where water and calcium ions reside. And so we do know that the sodium, if it goes into this structure, it's going to be in this interlayer region as opposed to other locations in the material. But what we don't know is the impact of the high alkali concentrations on the stability of these phases. So if we're looking at calcium silicate hydrate gel with sodium in it, or cash gel, where aluminium's in the gel as well, and then there's sodium in it, what impact does this sodium have on the propensity for the gel to dissolve, say, in certain environments, or react with carbon dioxide, which these phases do react with? So this information has potential implications for long-term performance of the concrete, specifically regarding the gel stability. And so what we did here was using density functional theory modeling to determine the impact of sodium on a crystalline model phase that's got very similar local bonding environments to calcium silicate hydrate gel. Because of the limitations with DFT, being able to get to really large system sizes, we know CSH is like a disordered nanocrystalline phase, but with the DFT, with the limitations of the system size, here we decided to model clinotobermorite, which has very similar local bonding environments to the actual gel, especially when aluminium's incorporated into the structure, because clinotobermorite tends to have some cross-linking between the interlayer regions. And we also know when aluminium's brought into CSH gel, you also get that cross-linking happening within the structure. It's known from NMR results. So here's some details of the DFT calculations. We use VASP, and particularly the well-known PBE functional. The initial thing we did was to optimize the structure of clinotobermorite, including water molecules in the structure, because that was unknown in terms of having an accurate structure. And then what we did for every single structure we created was we calculated what was called the cohesive energy for the structure. And so the cohesive energy for the structure gives you an idea of how much energy the system gains, or how it reduces the ground state energy by having the atoms bonded together in the structure as opposed to isolated atoms. So that's the cohesive energy for one structure. And it means that you're essentially then able to compare, if you compare cohesive energies, you're able to compare structures of different chemical compositions. And so what we did was we systematically replaced single interlayer calcium atoms with not just sodium atoms, but also hydrogen, because a previous investigation we did on tobermorite, on the replacement of calciums for sodium, found that if you charge balance not with two sodiums, but instead with a sodium and a hydrogen atom that turns into a hydroxyl, that makes the structure more energetically favorable compared to two sodiums by themselves. And so what exactly we're doing here is, this is the interlayer region in clibotobermorite. So we were taking superstructures of clibotobermorite and systematically replacing calciums for sodium and hydrogen atoms. What we found was kind of interesting. We found that it depends on the arrangement of the substitution as to whether there was an energy penalty for the substitution or not. So for example, here, if we're looking at a sodium to calcium ratio of the whole structure of 0.08, so some sodium has been incorporated for calcium, there's two different arrangements that you can get. Well, these are two that are shown. One that has quite a very symmetric distribution of sodium in yellow versus the calcium in blue, where these are all the calciums in the system. And here over here, there's some broken symmetry that's been incorporated. And actually, there is an energy penalty associated with a broken symmetry that's almost 4 electron volts relative to the structure. And so we found that this symmetry is very important. And so down here, what's shown are the most symmetric arrangements of sodium atoms in yellow, depending on the amount of sodium that's been incorporated into the system, where if all interlayer calcium atoms are replaced by sodium, you end up with this ratio of 0.25. So now what we're going to do is look at how stable these structures are relative to the baseline clibotobermorite structure that has no sodium in it. And that's what's shown on this slide. So on this slide, we've defined something called the formation energy of the substituted structure, but it's with respect to neat clinotobermorite, whereby we're taking the cohesive energy of the substituted structure and we're subtracting from it the cohesive energy of clinotobermorite, and we're left with this formation energy, where the formation energy, if it's at 0, then it's saying that the substituted structure is as favorable as the clinotobermorite. There's no like energy penalty for having sodium in your system. But as this becomes more negative, the way that we've defined this formation energy means that as it becomes more negative, it's showing that there is a higher energy penalty for having sodium in your structure compared to calcium. And so what's shown on the x-axis here is for the different levels of substitution of sodium. So small levels on the left, high levels on the right. And it's interesting to see there's this cutoff point whereby if you have a small amount of sodium in your structure, the structure tends to be as stable if you're looking at ground state energy compared with the original clinotobermorite. But once you go past about 0.1 in terms of incorporation of sodium for calcium in the structure, you're losing this stability. It's becoming less favorable in terms of a structure compared to the clinotobermorite. So this is kind of interesting as like, what is meaning that you can put some sodium in and be okay, but then there comes a point whereby the structure is just less stable overall. We think that this can mean if you want to incorporate sodium into a calcium silicate hydrate gel, you want to be careful with the amount that you put in there. Some is okay, a lot is not. So this is helping inform us when we look at essentially experimental methods of investigation, what might be a cutoff limit for the amount of sodium that can be incorporated into these systems. We also went on and did analysis of the structures themselves at different sodium incorporation amounts. I'm not going to show a lot of what we did do, but for example, here, we looked at the electron density contour maps of the bonding between silicate tetrahedra and how sodium in the vicinity of these silicate tetrahedra are affecting essentially the electron densities. And so at small amounts of sodium that's incorporated, there tends to be quite strong bonding still occurring between the sodium tetrahedra. But if we go to really high levels of sodium, we can see that the contour maps are showing bonding strength has weakened. So that's potentially one of the reasons why we're seeing really high sodium levels are not so great in these phases. We also looked at things like barriers for movement of sodium through the system and some other properties to get a sense of what is sodium's impact on the material. So that's for looking at sodium incorporation into these calcium silicate hydrate gels, where we used density functional theory on a model crystalline phase to get that information. So there seems to be an upper limit for the amount of sodium that you can incorporate into this model phase, above which the structure, there's an energy penalty associated with the structure. So it's likely, we can't say 100%, but it's likely that a similar limit exists for disordered calcium silicate hydrate gels, but that's still to be explored. All that I'm saying here is we looked at the clinotopomorite crystal structure, and that's where we saw the differences. Now, one thing that's a complicating factor on this is that we know when you incorporate sodium into the gels experimentally, you don't have exactly the same bonding environment in the substituted gels that you have in the original gels. And what specifically I mean here is we know that the silicate chains that exist in the gels will change based on the amount of sodium that's incorporated. And we wanted to get a better sense of this from an experimental viewpoint. So this is what I'm going to show now, is sodium incorporation into synthetic calcium silicate hydrate gels and the impact on things like the chain length and nanocrystallinity and some other properties. So this is the second aim. We are very interested in the gel, binder gel that holds concrete together, in its nanoscale ordering, so degree of crystallinity at the nanoscale, and its degree of polymerization when sodium is incorporated into the structure. So what is unknown is the impact of high alkali concentration. So a lot of sodium, what's unknown is how a lot of sodium impacts the molecular structure of these gels. And so because in Portland cement systems and in alkali-activated systems, the amount of sodium seems to be going up, especially for the Portland cement systems with things like recycled glass being incorporated. This is very important for thinking about how the material is going to perform long term. And then a second question we have, which is more of a kind of fundamental academic question, is people have in the past, to understand things like solubility of these gels, have always synthesized phase pure gels. But what is unknown is how representative are these synthetic phase pure gels of the actual gel that we find in the cement systems. And so that's one thing we're going to assess today in terms of structure, not in terms of like thermodynamics values themselves, but just in terms of structure of the material. Do the atomic structures look similar or not? Because the assumption that's been made is that the synthetic gels are representative of the real gels. So we'll look into that one. So this is an experimental study that we did. We made a whole range of synthetic gels with and without sodium and alumina in there. And we went to quite high amounts of sodium beyond which people have looked at in the past. And we wanted to look at the connectivity of the silicates in the gels to get a sense of how sodium, especially sodium, affects this connectivity. And we used both nuclear magnetic resonance, and we also used X-ray pair distribution function analysis. I found some interesting results there. And so if you're not aware of nuclear magnetic resonance used for studying silicate polymerization, it's very routinely done for a whole range of silicate-based materials. There's this QN notation that's used. So if you look at silicate units, if a silicate unit's not bonded to any other silicate units, it has a notation of Q0 because it has no neighbors. If there's one neighbor, it's Q1, 2 neighbors, it's Q2, 3 neighbors, it's Q3, 4 neighbors, it's Q4. So we're going to look at this degree of polymerization using NMR to get a sense of how especially sodium impacts the Q distribution of the silicates. So here's one example. I'm not showing all of the results, but here's one example where we synthesized phase pure gels with a starting overall bulk composition of calcium to silicon of 1. And then what's shown on this slide is the NMR spectra of silicon. And so we synthesized these gels in different sodium hydroxide concentrations, no sodium hydroxide, 1 molar sodium hydroxide, 5 molar sodium hydroxide. And the resulting solid gel that precipitated and we filtered out, we then analyzed with NMR. And so you can see that the peaks in the spectrum move depending on the solution conditions which the gel was synthesized under. And specifically what we see here is the center of gravity moves from more Q2 units for when we don't have any sodium in the system to more Q1 when we have quite a bit of sodium in the system. So this is showing that as sodium is incorporated into the gel, and we know that sodium is incorporated into the gel when we've done additional characterization, you become less polymerized for the gel itself. So the silicate chains are broken up more. And so if we look at a range of gels with different starting compositions and we plot this center of gravity value that we extract from the spectra, what you can see is when there's no sodium incorporated, we have relatively high degrees of polymerization for the silicate chains. But the more you incorporate sodium into the system, the more depolymerized those gels become. And so we knew what was going on around here, but the new information that we've really contributed to is what's going on at really high sodium amounts. And so this, you got to be careful with when it comes to sodium, because we are seeing there's quite a change between medium sodium levels and very high sodium levels. And so we want to be avoiding the types of gels that precipitate at these really high values. And I'll talk in a little bit about how we're going about doing that. We also studied these gels using high energy X-ray diffraction. Specifically, this was done at Argonne National Lab on 11IDB, which is a pair distribution function beamline. Most of you are probably aware of the technique of PDF analysis, but just in case you're not, it's a diffraction-based technique. So you're doing either X-ray or neutron scattering. You're collecting over the very wide Q range momentum transfer. It's very important for getting good PDF results. And then you're just Fourier transforming the data. And so you're going from reciprocal space to real space, same information, just displayed in different spaces. Us humans, we tend to be able to interpret better real space rather than thinking about, okay, what is the local structure of this slag in reciprocal space? It's very hard to understand. If you look in real space, then you're looking at bond lengths in the nearest neighbors, and then you're looking at atom-atom distances the further you go out. So this is a histogram of all atom-atom distances in your material. And so we did this analysis for the synthetic gels. And so here is the pair distribution functions for the same gels I showed you previously with the NMR. And so what we see here is this is tetrahedral silicon or aluminium, We have a bond length at about 1.65 angstroms. There's calcium in the system, especially. Actually here, the calcium actually goes up for when we're in the high sodium amounts. So there's quite a lot of calcium in this system, less in the other ones. And then we have atom-atom distances. So this is silicon-silicon, silicon-aluminium, aluminium-aluminium distances. This is calcium-silicon, calcium-aluminium distances, and you keep on going on. And so the one thing we did here, wondering about, is can we use this TT intensity to get a sense of degree of polymerization of the gel from a paired distribution function? I mean, NMR is the way to go, right? If you want to get very nice quantitative information on degree of polymerization for silicates, NMR, it's the state of the art. But we're interested to see what could PDF tell us about this. And so we plotted the intensity of that correlation for all the different samples synthesized under different conditions. And lo and behold, we got a very similar behavior to what we saw for the NMR results, which is kind of interesting. So higher degree of polymerization, higher TT peak intensity, lower TT peak intensity, lower degree of polymerization. And if we plot the X-ray intensity, that data, against the center of gravity from NMR, there is some kind of correlation that exists between the NMR and the PDF techniques. So this is more just a curiosity kind of result that we found, but we thought it was kind of interesting that even with PDF analysis, we can get a sense of the degree of polymerization, relative differences in degree of polymerization. And so what you see here is towards the right, you get a high degree of polymerization on this plot. Towards the left, low degree. And then if we look at the amount of alkali the gels were synthesized under, there's a low amount on the upper right. There's a high amount on the bottom left. So what we really want to do is be within the upper right-hand corner of this plot for when we're making the gels, because a more polymerized gel is likely to degrade at a slower rate compared to a less polymerized gel if everything else tends to be the same. And one thing I should say here is for Portland cement, this is the range that you get for the degree of polymerization. If you look at alkali-activated concretes, we really span a very wide range. So it's important to get a sense of degree of polymerization of the gels, because if you're down here, this might be an issue when it comes to long-term performance. And so the reason for this idea, well, let me go to the second part here first. So it's clear that the alkalis cause the silicate chains to depolymerize. So you get a lower QN value. Now, it's not directly shown, but you can think about the fact that if you have a lower QN value, it may make it easier for silicates to leach out from the gel over the time because they're not as strongly bonded into the system. In contrast to, say, if you have like a highly coordinated Q4 type arrangement of the silicates. And so this is what we've found, is that the more polymerized you have less sodium, the more sodium you have less polymerized. So we have resolved existing contradictions in the literature surrounding the alkalis and the degree of polymerization. Mostly in the past, people have studied both sodium and aluminium at the same time, where aluminium is known to increase the degree of polymerization. And so that's important to understand. One way of offsetting this depolymerization that occurs from the sodium is to make sure you have an ample source of alumina to incorporate into the system. And then the other thing is we went to quite high sodium concentrations, beyond which the community has looked at in the past. And we saw even further depolymerization occurring, which we need to be careful about when it comes to what properties the real gels have when we use them in a concrete. The last thing I want to talk about today is nanoscale ordering. So all of what I've shown experimentally was based on synthetic gels. And at the start, I mentioned that it's an assumption that people have is the synthetic gels are representative of the real gels in the concrete. So It's hard to look at this on a Portland cement-based concrete system because you have upwards of 7 to 8 crystalline phases, and then you have the disordered CSH type gel in there. So if you're trying to identify just what the CSH gel looks like in terms of atomic structure, it's very difficult because of all the other phases that give rise to scattering or any kind of bulk technique that you use. If we look at the alkali-activated slag system, we are lucky that we only have reacting glassy slag, which is a calcium, magnesium, aluminosilicate type glass. We have the Knasch gel that precipitates, and occasionally you get a very small amount of a secondary phase like a hydrotalcite like layered double hydroxide, but it tends to be in very small quantities. So what we've done here is actually compared the synthetic Knasch gels to the Knasch gel in an alkali-activated slag after we've subtracted the unreacted slag from the data. So what's shown here on the screen in the black, that's actually the real Knasch gel after we've subtracted out the contributions from unreacted slag. And then we've plotted 2 of the synthetic gels with different starting calcium to silicon ratios. And so especially if you compare the dark blue and the black, you see they're kind of similar up until about 4 angstroms. The light blue is a little bit different because it's got a different overall composition for the gel. But then what you can see is beyond about 4 angstroms, it's actually the 2 blues that become more similar. And then the black itself, which is the real gel, is a lot less intense. And so if we quantify how quickly the atom-atom correlations drop off as you look at increasing distances, we see for the synthetic gel, and this one's shown in purple, that the envelope in which it drops off is a lot slower in distance compared to the black curve. And so we can define what's known as a nanocrystallite type size for the gel. And if we look at a Knasch type gel, we end up with a size that's beyond about 60 angstroms. Whereas if we look at the real gel in the alkali-activated slag system, it's a lot smaller in terms of nanocrystallite size. It's 25 angstroms. So this is showing you specifically for these 2 types of gels that the synthetic gel is a lot more ordered. It has an increased degree of crystallinity compared to the gel that we find in the alkali-activated slag system, which is, there's a couple of things that come out of this. The first thing is a greater degree of crystallinity can imply, there's always caveats to this, but can imply increased thermodynamic stability. So say if we're looking at 2 types of silica, amorphous silica versus crystalline quartz, they're both silica, they both have the same local atomic bonding environment, they both have Q4 silicate network, but if you look at the solubilities, they are different. And so these results for the gels could indicate that there is differences in terms of thermodynamics between the synthetic gels and the real gels, though this is a hypothesis that we have based on these results. And therefore, you know, if we were to confirm or want to investigate more, a lot more research would be needed done to either support or contradict this hypothesis that we have. Okay, so nanoscale ordering implications. Well, from an academic standpoint, a lot of people in the cements community for thermodynamic modeling rely on the thermodynamic data for synthetic gels. And so the question here is, because of the differences in degree of ordering we've found, there could be differences in the thermodynamic properties. And so therefore it's probably worthwhile looking at real systems if that can be done to extract out thermodynamic data and then compare them to the synthetic systems. But one thing is, if this is the case, if this is true in terms of differences in thermodynamic stability, there's an opportunity here to actually manipulate the nanoscale ordering of the gels that precipitate in the real systems. And this might not be so easy for Portland cement concrete, just because of how complex it is to try and then assess how you can manipulate the nanoscale ordering of the gel. But especially for the alkali-activated concrete, it could be possible if we could manipulate what types of structures form for these gels. We could potentially make them more stable over time, increase the durability of the material, and even further work out ways to increase longevity so that we're not having to replace concrete so often when it starts degrading in the environment. So I know it's gone to 150. So I'm going to end. I had a whole other set of presentations, but we're not going to do that. So what I'm going to do is go to the end of all of this and find my acknowledgement slide, thank funding sources, facilities that was used to collect this data, collaborators on the projects, and the actual students and postdocs that did the research. I'd be happy to take any questions, and thanks for listening.
Thank you so much for this very clear talk. And I think it was very educational for all of the students too, looking at all of those detailed characterization techniques. So thank you. We will open the floor for questions now, and I'm going to take a look at the chat. There is the first question by Caitlin. Can you unmute yourself and please ask your question?
Yeah, I was wondering, when you were looking at the PDF results, why did you specifically single out the TT peak and analyze the TT peak?
So from the atom-atom correlations that showed up for our system, if we're trying to work out which one is most appropriate for degree of polymerization, it would be that TT peak, because it's essentially telling you how many linkages you have between silicate tetrahedra. So you can think, if you have like silicate tetrahedra in your sample, but none of them are connected, you would be a Q0 according to NMR. So each silicate wouldn't have another silicate neighbor. And then if you think about the actual distances between the silicate tetrahedra, they would be longer than what needs to contribute to that TT peak at about 3 angstroms in our data, which means that as you go up in degree of polymerization, the more of these TT distances that show up at about 3 angstroms, and so that peak becomes more intense. So that's why we chose that correlation to compare with the NMR data, because it's likely, well, there's going to be other TT distances that turn up in the PDF data, but it's we knew that that correlation at 3 angstroms was one of them, and we weren't sure further out in the PDF data which correlations would also give rise to that information. So that's why we chose the 3 angstrom one.
Okay, thank you.
You're welcome.
I add a question to this because it's about the same data set, the PDF data that you showed. Did you look maybe to figure out if there is a correlation with any of the other peaks that stand out with your NMR data?
We didn't do that for this data, no. And that's one thing when it comes to trying to interpret pair distribution function data. It can be tricky if you don't have a structural model, or if you're not, I mean, you can do like linear regression analysis with different peaks. So one thing that we are doing more nowadays is comparing DFT structures and force field based structures to experimental data to try and better interpret the atom-atom correlations, especially past about 4 angstroms, because up to about 4 angstroms, you can get a sense from knowing the chemistry and the, other experimental data, you can help to interpret that. But beyond that, it becomes a lot harder. So
Yeah.
We're moving towards structural models to help interpret that.
Okay, great. Thank you. Shantanu had a question. Please unmute yourself.
Yeah. So you can hear me, right?
Yep.
So I have a question regarding NMR. So can you please show me the slide that you have collected NMR data?
Yep, sure.
Yeah. So my question is like, what kind of functionality that the silicon centers do you have? Because when I had recorded NMR spectra for silica, so I used to get Q4, Q3, and Q2 at the chemical shifts from like for Q4, it was around -110.
Yep.
For Q3, it was somewhere around 100. And for Q2, it was somewhere around -92. So, but at that time, the neighbors that you're talking about, so in silica, we had silanols and siloxanes. So, and here I can see the chemical shifts are significantly different from what I had got.
Yeah.
So I'd like to know the functionality of the silicon centers.
So the silicon centers, there is a lot of interactions with calcium ions around the silicon centers, like away from the silicates. And then also in terms of hydroxyls, there's probably not too much going on in there. People have looked at this quite extensively when it comes to cements and NMR analysis. So I fully understand in terms of like peak positions, they can move based on, you know, the local environment around the silicon centers. What I will say is that when it comes to the assignment of these peaks, that came from looking in the literature with the existing analysis of similar synthetic gels that people have done in the past. And we were doing this in collaboration with Jorgen Skibsted, who does a lot of cement NMR analysis out of Denmark. So beyond that, in terms of exact information, I can't provide it right now, but fully aware of how, you know, it's the local bonding environment around the silicon centers that can change where the chemical shift is. And so the way that this was assigned with my postdoc was based on his existing knowledge with NMR, working with Jorgen Skibsted, and also literature data as well.
Okay, thank you. Thank you very much. Excellent. Yeah.
Thanks.
All right, thank you. Let's move on. Arash has a question, and I apologize if I'm saying any of the attendees' names wrong.
Thank you. No, you're right. It's Arash. So thank you so much, Dr. White, for your presentation. Like as a person who is working like in alkali-activated material for about 4 years now, but mostly from practical point of view, like I'm in the civil engineering program and then geotechnical part. So most of the times I'm just trying to deal with the material and then try to get a strength I'm looking for. And then sometimes even when we are looking for the material and they're trying systematical trial and errors, and then we don't get the strength we are looking for. Sometimes we don't have the knowledge of the material point. And then we say, oh, okay, it's not working, it's low reactive, high reactive. But I really like the way you're looking at the material scientifically in detail, how the microstructure of the material. This is really amazing. But my question is, you're just answering the problem scientifically. I mean, from the material science point of view, or you're looking for some practical things too, like you're trying to develop some durable, high performance geopolymers, or it's better to say.
Yeah, I mean, that's an interesting question. So there is some funding in my group that's more on kind of like the applied side. So for example, we're looking at trying to make ultra acid resistant alkali-activated metakaolin samples by manipulating chemistry of the system. And in that comes a lot of more of the applied side as well. So strength and pore structure and setting time and all of that. But part of that is we're trying by understanding things such as, okay, the gels might be quite amorphous. Are there ways we can manipulate the crystallinity of the gels? So maybe not make them crystalline, but can we make them nanocrystalline? That could potentially influence durability, right? How stable the gel is and make it more resistant to acid degradation, for example. So that's kind of how we're going about the research, is trying to connect the fundamental material science findings with, okay, if we can understand this more, what could we manipulate now or optimize now to impact more macroscopic performance, which, you know, that's what industry is all about. But it's very, you touched on a very relevant point, which is, so what? If you find out all this fundamental stuff, so what? And it's, you know, how to then transform those findings into potential solutions at a more applied level.
And the other thing is, it was interesting in one of your slides, you mentioned about how the neuron spectroscopy is better than XRD in detecting the amorphous phases. I had several issues, like when I was doing the, because most of the times we just, when we are doing practical things, we just use XRD just because it's cost effective than like the other methods. And the knowledge part, I don't have any familiarity with that. I always had a problem with the detection of the amorphous phase using XRD. And now I'm finding that, okay, it's better to use other methods like this.
It is. The only caveat there is the method that I was talking about with pair distribution function analysis. You can't do it using a normal XRD instrument. We did our experiments at large scale facilities, like at a synchrotron. So there are caveats, there are drawbacks to trying to get additional information. Sometimes it's not as straightforward as kind of the stock standard techniques that people use to analyze cement systems. So it's a trade-off. It is a trade-off.
Yeah, thank you.
You're welcome.
I love that you're using synchrotron data to do pair distribution function analysis. I think that's really cool. Could you use, and that might be a naive question, could you use Raman spectroscopy to look at these types of materials? Is that something that the community does?
They do, yeah. I mean, it's not as common as, say, FTIR. You see a lot more FTIR data turning up than Raman, but there is certain groups that use Raman quite extensively to look at things like the silicate environments, to look at connectivity of the silicates, those kind of things. And then I'm trying to think what else there is in terms of what people have done. I mean, the more complementary techniques you put together, the more you understand about the material.
Sure.
Right.
Yeah.
And so therefore, it's just making sure you're using techniques that are applicable to answer the questions you want to answer. And so for us, that's been a lot about local structure changes in situ. So we do a lot of in situ synchrotron techniques, and that's kind of nice to look at both how the systems form and then also degradation mechanisms as well.
Yeah.
But yeah, it's very, I mean, it is very true that there are a range of techniques out there that can help answer questions from various viewpoints so that you fully understand what's going on in the system.
Absolutely. Yeah, great. And for the in situ, do you mostly do temperature dependent or also like different? I could envision that it's also very much dependent on like water in the air and stuff like that.
Yeah, I mean, all of the above. So we've done formation-based in situ reactions. So if you're making a cement, what happens when you've just mixed it up, and you watch what happens with the dissolution of the starting phases and what precipitates out. We've done high temperature work. So what happens with certain types of cements on high temperature? What phases form? Does it decompose or does it crystallize? These kind of things. And we also do reactions with cured pastes and say CO2 gas, because CO2 actually degrades phases in concrete. It's, not everyone knows that, but it does. It's an aggressive molecule. And we've also looked at like impact of sulfates on cured cements as well, and what kind of reactions occur there. So I think it's more about how you can envision setting up doing the actual experiment as to whether it's feasible to do that kind of analysis. And that's where creating sample environments, like simple sample environments, can really help you look at in situ processes.
Yeah, that's really interesting. I have another thought on that, but I will send you an email if that's okay.
Oh yeah, sure.
Moving forward, since I do not see any other questions in the chat, so, and we are past the hour. So let me just say again, thank you so much for joining us. I just had to remember we had one of your colleagues, Leslie Schoop, actually on campus for one of our last School of Molecular Science seminars, roughly a year ago. She was here, I think it was Valentine's Day a year ago, that's why I remember it.
Oh, wow.
And now we have, and now we have another excellent speaker from Princeton. Sadly only remotely, but I think it's great. We had, I should point that out, we had around 100 participants online today.
Oh, nice.
It's one of our records, I would say, for this seminar series. So that was great. And let me maybe introduce quickly Ankit. He's one of our organizers. He's an ASU colleague of mine. He's online and
Hi, Claire. Nice to see you. Yeah, and it was really a learning experience for me as well, because I'm essentially a metallurgical engineer, but I do sort of collaborate sometimes with ceramics people. So it was very like I got a lot of information about this material that you work on.
Oh, great! Thanks. Nice to meet you.
So, and with that, thank you so much again. I hope you have a great rest of your Friday, everybody that is still on. And thanks for joining us as always. And have a good rest of your day, everybody.
Thank you. Bye.